Okay, so a problem that you're bound to see in nearly all of your physics tests, or in the physics final, or all of your physics tests on this unit, is going to be this gradient problem. And so essentially what we have here is we have a mass of m mass, right? And then it's on a gradient of gradient theta. And the question will usually be, the question depends really on the situation, but after this I'm hoping you'll be able to answer all the questions. But in this question, we're just going to ask, what's the acceleration of this box as it goes down this gradient? Because it will have a constant acceleration, as we will discover very soon. So before we get into it and really try to understand where the acceleration is coming from, the first thing we always need to do is draw ourselves a free body diagram. So of course we have ourselves a mg coming down as usual. We have ourselves a normal force that's being exerted in the direction perpendicular, or rather normal, to the surface it's on, which is this gradient. So I'll draw Fn, if I can draw it small enough. And okay, that's good enough. And those are essentially the main forces we're going to have on this box. So if we were to consider this, let's first consider how this would work in a world where there is no gradient. If we just had a box of mass m, and it was falling down, then we know that the force on it would be mg, right? Because that would come directly from the center, and thus the acceleration would just be g in this situation. However, the difference here is that we have this gradient on it, and this gradient means that it can't go down. There's no way for it to go down. But the only direction, rather, that it can go is this way, parallel to the gradient. So that's how we'll see it move. And not surprisingly enough, we'll find that, or actually surprisingly enough, you'll find that not all of mg will actually then be used to push this down the gradient. Rather, only part of it will be used to push it down the gradient. The rest of it will be used just as the weight of the object on this gradient. And so let's try to see how that would look. If we look at the components, let me draw this a bit bigger. I'll draw it here in the center. I'll draw it in a nice pink color. If we look at this box, right, it's going down with mass m, and we're getting real up and close here. And we have our mg that's going down. So essentially what we want to do is find the components of mg that is going in this direction, because part of mg will be going in this direction, which will be resulting in the normal force, or which will be equivalent to the normal force, and then part of it will be going in this direction. And this is let me do that in a nice red color. This is the only part of mg that we care about, because this is the only part that's going to contribute to it accelerating. The force of it going this way is not going to contribute to its acceleration at all. So the question is, how can we find this force here? We know it's a component of mg, but how do we get that component? Well, if we think about it, the component of mg going in that direction is going to be a portion or a component of mg, right? And that will be dependent on this theta. If this theta is bigger, we could see that more of mg will go towards pushing it down the gradient. If theta is smaller, we'll see that less of mg is making it accelerate. Like, just to give you some intuition for that, if you have something that's super small, maybe this is a 1 degree incline, theta is 1 degree in this situation, we could imagine that this will move slowly, or it may not even move at all. And we'll get to why it won't move at all. It's due to friction, but we'll get to that later. That's outside the scope of this video. But we're going to assume this is in a frictionless environment. Let me just add that. No friction. No friction. I'll make a video later where we account for friction. So let's see, how do we calculate this yellow component here? Well, this, if we draw a triangle, here parallel to MG, and then parallel to the direction it's going in, and we draw a right angle here, and we extend these out, we're going to see that this angle here is just theta. These are similar triangles. And so thus this angle right here, assuming this is a right angle, this angle here has to be 90 degrees minus theta, right? Pause this if you don't agree with that, but this needs to add up to 180 because it's a triangle, right? So that means that, let me just erase this so we don't have to look at it, but that means that the component of MG, if we draw this triangle here, we'll say this is MG. This is the direction it's going. We know that this is 90 minus theta. We want to make MG the hypotenuse of this triangle that we're about to draw, because we're trying to find the components of it going in certain directions, and if it's not the hypotenuse, we won't be finding the components of MG. Rather, the MG will be a component of the new hypothesis that we're making, right? So we'll just complete this triangle, keeping MG as the hypotenuse, and this will be our right angle. And so then, using this information, we can make the following statement. We can say from this, we can't see that color. We can say from this, we can say that if we take cosine of 90 degrees minus theta, which is just this angle here, it will be equal to adjacent over here, which is actually the component we're trying to find, over the hypotenuse of this triangle, which is just MG. This gives us that the component that we're trying to find is MG cosine 90 degrees minus theta. And this is essentially it. This is the component we're trying to find. So we can stop here, or we can just simplify this a bit more. Because if you remember from your trigonometry or algebra 2 classes, you might remember that 90 minus an angle, if you put this into a cosine, is equal to just that angle in terms of sine. So this is really just equal to mg sine theta. This is because complementary angles will have the same, if you have one angle and the cosine of that angle will be equal to its complementary angle, the sine of that complementary angle. So this statement is essentially what we need to know. So this gives us that this arrow here, from here, is going to be equal to, that component of mg is just mg sine theta. And as you play around with this is something you'll probably want to memorize, so you don't have to rethink about it each time, or as you do a few of these, you'll sort of get the hang of it and not really have to rederive this formula each time. But it's good to know where it comes from, and it'll work in essentially all scenarios when you don't have to deal with friction. And when we deal with friction, we're just going to be adding on something to this. This will still be the main component of the formula. So with this in mind, we can start to determine our answer of what the acceleration is. So if we come back to Newton's second law, F net equals ma. We know that ma is going to be mg sine theta. Right, mg sine theta. We can then solve for this acceleration, which is what we're trying to solve for, which will give us that the acceleration a is going to be mg, let me do this in yellow, is going to be mg sine theta all over the quantity m. And if we pull out some cancelization, we'll see that the m's go away. This will yield us the answer. G sine theta is the acceleration of this mass. And so this is actually our answer right there. As soon as you plug in whatever sine theta is, you'll find the acceleration. And something just to ponder about if you have a moment is to think about how mass has no effect on the acceleration of this object, just as it has on a gradient plane, just as it has no effect on the object when it's just free falling. So that's something to consider. And remember, when you use this formula, this is for a frictionless environment. No friction. So with that, thanks for watching, and I'll see you soon for this same thing but with friction.